We have a dipole in a uniform electric field. Part A is asking for which orientations of the dipole is the net torque on the dipole going to be equal to 0. Now let's remember the formula for net torque acting on a dipole. Torque vector is equal to the dipole moment vector cross product the electric field vector. Now a cross product is equal to 0 when the angle between the two vectors is either equal to 0 or 180 degrees. Another way to think about it is to remember the magnitude for cross product. Magnitude here is going to be equal to P times E times sine theta, theta being the angle between the dipole moment vector and the electric field vector. Now, when is sine theta equal to 0? Sine theta is equal to 0 when theta is equal to 0 or when theta is equal to 180 degrees. So then we want our dipole to be oriented such that the dipole moment vector is either parallel to the electric field vector or anti-parallel to the electric field vector. And here's what the dipole would look like. The one on the left hand side has its dipole moment vector parallel to the electric field vector pointing right, and the one on the right hand side has the opposite direction. The dipole moment vector point is anti-parallel to the electric field vector. In both cases, sine theta is going to be equal to 0. So in the first case, theta is 0. In the second case, theta is 180 degrees. In both cases, sine theta is equal to 0, and net torque on the dipole is equal to 0. Part B is asking which of these is the stable state and which one is the unstable state. Answer this question. Imagine rotating each dipole slightly from the current orientation and try to figure out what it will do next. If the dipole tends to rotate back, that's a stable orientation. If after you rotate it slightly, the dipole continues to rotate in the same direction, that's an unstable orientation. So let's focus on the first case. I have rotated the dipole slightly in the counterclockwise direction. Now there's going to be a net torque on this dipole. There's going to be a force on each charged particle. There's going to be a force on the right hand direction on the positively charged particle following the direction of the electric field, whereas the negatively charged particle will experience a force in the opposite direction to the left. These two forces will create a net torque in the clockwise direction. So we have rotated our dipole in the counterclockwise direction, and immediately there was a net torque in the opposite direction, clockwise direction. So our dipole is going to rotate back to its original orientation. So this one is a stable orientation. Now imagine rotating the second dipole slightly, let's say in the clockwise direction. And again, the positively charged particle will experience a force pointing right, and the negatively charged particle will experience a force pointing left, opposite the direction of the electric field. Now, these two forces will create a net torque in the clockwise direction. Now I have already rotated my dipole slightly clockwise, and now there's a net torque in the clockwise direction, so my dipole is going to continue to rotate in the clockwise direction. That means this one is an unstable orientation to begin with. To answer part C, we look at the dipole's own electric field. Now, the pink electric field in the picture is the external electric field. It has nothing to do with the dipole. Now, the dipole itself also creates an electric field. The electric field of the dipole will point from the positive charge towards the negative charge, like so. For the stable dipole, the electric field created by the dipole itself then points to the left from the positive charge towards the negative charge again, which points in the opposite direction as the external electric field. Of course, the electric field created by the dipole is not uniform. The arrow that I show here is only the electric field orientation in between the two charges in the middle. But as you go away from the two charges, the electric field lines will be curved. But at any rate, in between, or in any direction, the electric field of the dipole will point from the positive towards the negative charge, which is opposite the external electric field.